Right, so for the final talk of today, it's a pleasure to have Natalia Pinzani-Fokeeva talking about horizon symmetries, hydrodynamics, and chaos.
All right, I would like to thank the organizers for giving me the opportunity to speak online, and I apologize I was not able to come to the conference. And I have more recent work that it's about first order phase transitions and neutron star mergers from a top-down holographic model, but I thought this older work is more suitable for this conference. So some of you may have seen it already, so sorry for that. Okay, so this is work I've done with Hong Liu and Maria Knish, and we have some work in progress as well. It's about horizon symmetries, hydrodynamics, and chaos. So let me put first this topic in a context. So the context is that of asymptotic symmetries. Asymptotic symmetries are symmetries that don't vanish at the asymptotic boundary of the space-time and preserve some boundary conditions. So notable examples are the BMS group in flat space-time, conformal group in anti-de Sitter space-time, and they are very well studied and very well understood to a certain extent. They can be interpreted as the symmetries of the dual theory living on the boundary of the space-time. So if the space-time is anti-de Sitter, the symmetries are that of the conformal group, and are the symmetries of the dual space-time. And if the space-time is flat, the symmetries at the asymptotic flat space-time are the symmetries of the putative dual field theory that lives on that boundary. So they have also been helpful in the context of, for example, celestial holography in trying to understand what would be the dual field theory of flat space-time. And they are also related to physical phenomena like soft graviton or photon theorems, memory effect, and so forth and so on. Okay, so but instead of, do you see my cursor if I do that like this?
Yes.
Okay.
Yeah, we can see it.
Okay, so instead of just considering the asymptotic boundary, another boundary that we can consider is the horizon of a black hole, let's say. And people have studied horizon symmetries. So these are, again, local symmetries, like diffeomorphisms of the bulk, that do not vanish at the horizon boundary and preserve some boundary conditions. And these people have shown that there is killing horizons. Black holes, isolated black holes, possess an infinite amount of killing, possess an infinite amount of symmetries beyond the usual killing symmetries. And in fact, not just horizons, but any null surface possess an infinite amount of these symmetries, and they can be characterized covariantly. Okay, that said, while the asymptotic symmetries that are defined at the asymptotic boundary of the spacetime are quite well understood, and their interpretation is well understood, the symmetries defined here are not very well they are not understood at the same level. In fact, even trying to understand what are the symmetries from the point of view of the asymptotic boundary is unclear. Okay, so, and this is precisely the goal that I have in this paper, or today in this work, is trying to give an interpretation of these horizon symmetries of black holes. And the interpretation is going to be in terms of symmetries of the dual hydrodynamic and chaotic boundary theory. So in order to get to this point, I first have to give you what are these horizon. I have to explain what are these horizon symmetries, and then I'll get to the interpretation. Okay. So let me start with this review of what are these horizon symmetry and explain what I mean by new horizon symmetry. This is also a little bit of a new result. Okay, so as I said, I want to consider horizons, and I will have in mind black hole horizons, in particular planar black hole horizons. But a lot of the statements that I'm going to say are general to null surfaces. But I will always call them horizons, although the title is null surface. So if we consider, we want to study a null manifold, so a null surface, and a null, and we will consider a bulk spacetime that has coordinates xa and a metric gab in the bulk. So this will be our bulk representation, and this will be like the future horizon of the black hole, and this will be the past horizon. In particular, we are interested in this future horizon. So now we consider embedding functions, this big X of sigma. So sigma are coordinates on the horizon surface, and X of sigma are the embedding functions, or in other words, how the horizon manifold is embedded in the bulk manifold. So you can define an induced metric on the horizon via the bulk metric and these embedding functions. The fact that that makes this surface null is that there is a degenerate direction. So there is a vector for which this condition is satisfied, so that there is a zero eigenvalue. So these little a, b indices are intrinsic to the horizon, and the big a, b indices are the bulk indices. So the null vector here is defined on the horizon, and then you can define the quantity in the bulk by performing the push forward of this horizon quantity. And this symbol means that you evaluate this quantity at the horizon. And therefore, this bulk null vector is null because of the usual condition that it has a zero norm at the horizon. The other important quantity that we want to keep track of is this non-affinity parameter k, and it's defined through this relation, which basically tells us this is the non-affine parameter of the null geodesics that are defined on this surface. Okay, so these are all the definitions that I need for null surfaces. So now I'm going to tell you about horizon symmetries, and I should put an asterisk, do you say? I should put a disclaimer here. These are going to be redundant. What I'm going to talk about are redundancies, not really symmetries of the horizons, in the sense that I'm not going to see conserved quantities and conserved equations of motion. But nevertheless, I'm going to stick to this terminology because this is what you encounter in literature. So let's consider bulk diffeomorphisms. So these are diffeomorphisms in the bulk, and they transform the metric as usual. So these are linearized. In particular, here consider the linearized transformations. And you can choose to either transform the metric, this active formalism, or transform the embedding coordinates. So here I'm choosing to transform just the metric, so one or the other. And therefore, this transformation implies a transformation also of the horizon-induced metric in this obvious way. But they don't modify, in principle, the definition of this quantity here, because that's just defined as being the null thing that satisfies the null condition before. While the non-affinity parameter definition changes because of the change inside this covariant derivative. The metric is contained here inside. So this changes. So then what we define is that this bulk diffeomorphism is a horizon preserving diffeomorphism if these two conditions are satisfied. Basically, that the null manifold remains null and the non-affinity parameter is unchanged. So these two give these two conditions. So what I said is that you take the bulk diffeomorphisms, you impose boundary conditions on the horizon, these two conditions, and this restricts the amount of symmetries that I have through these horizon symmetry constraints. Okay, so let's unpack a little bit these constraints through a simple example. So we consider now diffeomorphisms that lie only along the horizon. So this condition tells us that it multiplies the bulk diffeomorphisms on the L subscript A in the lower, with the index lower, that's the null vector orthogonal to that surface. And we are saying that in the orthogonal direction, there are no diffeomorphisms. And let's choose some specific gauge choice for how the horizon is parametrized, meaning that we choose the null direction to be aligned with this with the time direction. And therefore, the horizon metric is just given by the spatial metric with the spatial indices. So with this parametrization of the horizon coordinates, the diffeomorphisms, the ones which are along the horizon, can be simply, I choose to write them in this way. So these are the linearized diffeomorphisms. They're called, and we name them with as super translations and super rotations. These are just names that that are taken from the BMS terminology because they look quite similar. But importantly, if I look now in this parametrization, I look at what are the horizon symmetry constraints. They are these ones now. So this is how they become. So this is a constraint on the super rotation, and this is a constraint on the super translation. So this is means that these horizon symmetries are restricted by how I impose the boundary conditions. And they lead to this transformation. So see, this one tells us that the time derivative of this quantity is 0. And therefore, this thing only depends on the spatial coordinates. And this one tells us that there is this similar time-independent mode and also this exponentially decaying transformation. Okay? So this has been derived before by these people in some other language because they used a non-covariant formalism and used Gaussian null coordinates, etc. Okay, so let me do one more step and relax a little bit this condition here. So let's not only consider the symmetries along the horizon, but allow the more general diffeomorphisms that may shift the location of the horizon while maintaining the constraints that I chose to define before, this horizon preserving diffeomorphisms. And again, in this simple coordinate choice of the horizon coordinates, this is how this symmetry looks like. We have these bits that we have before, and we have these additional pink parts, the exponentially growing part. Okay, so this part, because we chose to relax this condition here, this is the new horizon symmetry. And what we are going to see next is that this part here is going to be interpreted as the hydrodynamic degree symmetries of the dual field theory. And these are going to be interpreted as the symmetries of the dual chaotic system. And this part, and these two were somehow postulated before in some papers, while this one here is a new prediction that we have. So I'm going to pause to see if there are some questions. I don't see you, so if you speak up, okay. Okay, so if there are no questions, I can proceed. So let's go to the interpretation. But in order to give you precisely the interpretation, I need to explain what is, in terms of hydrodynamics and chaotic boundary theory, I have to explain you the bits that are necessary to understand this interpretation. So let me pause on this hydrodynamic bit first. So hydrodynamics is an effective field theory of macroscopic fluid elements, as long as there is a separation of scales. So that there is some, we're considering length scales that are much bigger than the, for example, the mean free path, the path that the particles take before subsequent collisions. And the usual degrees of freedom are pointwise. They are associated not to a single particle, but to fluid elements, which are sort of like macroscopic objects that contain an Avogadro number of the microscopic constituents, but are still infinitesimal enough that we can treat them as effectively point-like. And the usual degrees of freedom are the velocity, the temperature, and if you have a charged fluid, you also have a chemical potential, and so forth and so on. But actually, it has been realized that if you want to write an effective action for hydrodynamics, so instead of just considering the hydrodynamic equations of motion, you want to derive these equations from an action principle. The more convenient degrees of freedom are the fluid maps themselves. So let me explain. So are these ones here. So, and these come from considering hydrodynamics as existing in a fluid frame and a laboratory frame. So there is this space-time here given by the sigmas, and each point here is a specific fluid element. And then this other space is the space-time, the laboratory space. So each point here represents a physical place in the laboratory. So if we pick a specific element here and we follow this map through time, this will map a word line of the fluid element. So this is what this map is defining, like the word lines of fluid elements. And this is, if I write my effective action in terms of these variables here, it is possible to show that the variation of this action and imposing also diffeomorphism, invariance, etc., the variation of this action with respect to these variables will give us the equations of motion for hydrodynamics. So these are the conservation of the stress tensor, which is the relativistic generalization of the Navier-Stokes equations. And this is the current conservation equation if we have also a charged fluid, and this would be the corresponding map. And importantly, the actual velocity and temperature are now can be defined through these maps as the, let's say, the derivative of this map with respect to time. So basically, it's like the time derivative of this map will give you this thermal vector, which is whose normalized, the normalization of this vector is related to temperature, and the unit time-like vector is electricity field. But notice that by using these maps, we have introduced a redundancy. And this is a bit similar to what you do in electromagnetism when you deal with the electric field and the magnetic field. The correct variable that you have to use at the level of the Lagrangian are not those, but it's the gauge field. And by writing things in terms of a gauge field, you introduce this gauge redundancy. And here it's a little bit the same thing. So we work, if we work with hydrodynamics at the level of an action, we write things in terms of these more fundamental variables, but they come inherently with this redundancy here, which I've written in green. You can stare a little bit at this symmetry transformation, and you will see that it implies that this beta mu, this vector field, is invariant under this transformation. So it's a little bit, this plays the roles of the electromagnetic field, and this plays the roles of the gauge field in that analogy. Another simple intuitive explanation is that I have motivated to you this space-time each point represents a fluid element, but if I call this green element and this blue element, the naming is not important. I can reshuffle the name of the fluid elements and the hydrodynamic system will still be the same. So this is basically a redefinition of how you name the fluid elements and how you name the proper time in the fluid space. And it turns out that all this construction that I just gave you a glimpse of, so this local symmetry plus properties of the Schwinger-Keldysh path interval plus derivative expansion gives you a well-defined effective field theory for hydrodynamics. Okay, so I'm going to pause again if in case there are questions on this part. Okay, so let me tell you now about the chaos part of the boundary theory. And so this goes like this. So before I told you that hydrodynamics is an effective field theory that requires a separation of scales between the some long wavelength fluctuation and some microscopic scale. In a strongly coupled CFT, so I have in mind like holographic theories, this mean free path scale is related to 1 over temperature. That's basically the scale of this type of theories. And usually therefore you require this condition for the separation of scales. But in principle, you can extend formally and write hydrodynamics to all orders and reach the scales of temperature. This is what you can call quantum hydrodynamics in the sense that you write hydrodynamics to all ordering derivatives. You can do this in the Schwinger-Keldysh effective field theory formalism if you restrict yourself to quadratic perturbations. So if you write such a theory of quantum hydrodynamics, which is just hydrodynamics to all ordering derivatives, so it extends to this scales, the order of temperature, and you also impose the shift symmetry, both of these things, these exponentially growing and decaying conditions, transformations of this sigma zero variable, then what you get is an effective field theory for maximally chaotic systems, as these people have shown. There is an asterisk here because this has been done only in 0+1 dimensions when there is only energy conservation and no momentum conservation. And the predictions of this theory is... Yes?
Hi, it's Blaise. Can I ask a question?
Yes, sure.
That second bullet point, it must also have some fine print, right? You wouldn't expect that for a generic system, hydrodynamics can be extended to all order in derivatives to scales of order temperature. It has to break down.
Yeah, so here I'm assuming strongly coupled CFTs. So you just have this, it basically only has this type of, there is only this scale there that you have. And formally you can write it. And it seems to give you what you want in these strongly coupled CFTs. Of course, if you don't have this type of systems in mind, it won't work. I agree.
You mean holographic CFTs?
Yes, yes.
That's...
Okay. So, and the predictions of these types of theories, indeed for holographic CFTs, which is quite highly tied to this maximally chaotic assumption as well, or large N assumption, it's all intertwined. But at least for this type of theories, what these people have showed is that these type of theories will give you an out-of-time ordered correlation function that has this growth in time with the characteristic Lyapunov exponent and butterfly velocity. For those who don't know about this theory, so this is it's a question in the literature to understand what are quantum chaotic systems, and in particular, it's interesting to understand if I give you a system, you should be able to tell me whether it's chaotic or not. And it turns out that for this type of holographic type theories, like semi-classical theorems, a good probe of the chaotic behavior, the quantum chaotic, well, the semi-classical chaotic behavior, is this correlation function, which is a 4-point function. And it's mimicking the butterfly effect that appears in classical chaotic theories. So in classical chaotic theories, you look at nearby trajectories that if you change a little bit the initial conditions, they will grow apart at exponentially low. At some point they will grow apart. And this definition here, it's mimicking that behavior. So, and you look at this correlation function, and it has this exponential growing behavior. So basically, I give you a theory, a system, and you check this out of time order correlation. And if it has this behavior, you will tell me, oh yeah, this system is chaotic with this strength, the Lyapunov exponent, and the butterfly velocity property. Of course, again, this is a little bit restricted to these semi-classical systems. But this is a 4-point correlation function, and it's a bit difficult to compute and also a bit difficult to experimentally realize. And what other people have done is to actually they found a way to characterize the chaotic behavior by means of another probe, which is a 2-point function instead. So a correlation function of the energy density operator. And it turns out that if you have, at some point, a structure of this form, I'm being very schematic here, so I'm sure that there are other ways to write these correlation functions. But to be schematic, the form is like this, that there is at some point in omega and k, there is a structure that is of the form 0/0. And therefore, this correlation function becomes ill-defined. Or in other words, the would-be pole that appears here is cancelled by a zero of this, by a zero, and therefore the pole is skipped. So that's why the name pole skipping phenomenon. And it turns out that for these chaotic theories, you can compute this energy density correlation function in holography, and the location of the pole skipping point, so this omega star and k star, are precisely related to the Lyapunov exponent and the butterfly velocity in this way for maximal chaotic theory. So lambda is really 2 pi t. So, and this quantum hydrodynamics plus shift symmetry that these people have considered precisely realizes these 2 points. So it gives that as a prediction. And the important part was this exponentially growing and decaying symmetry. So this was the part that allowed you to have this pole skipping phenomenon and the exponentially growth of the out-of-time ordered correlation function. And in particular, no growth of the time-ordered correlation function. Okay, so are there questions on this part? Okay, so let me get to the final point. So after this excursus on horizon symmetries and hydrodynamics and chaos, let me connect all of it and try to interpret these horizon symmetries as symmetries of the dual hydrodynamic and chaotic theory. So for that, I will need to build the holographic dual of the fluid degrees of freedom. So these fluid degrees of freedom that are maps between some fluid frame and some space-time. In holography, the fluid frame is played by the horizon, as you may imagine by my notation, and the space-time is played by the asymptotic boundary. So here I'm considering indeed anti-de Sitter space-times and holography. But the only thing that I really need actually is that I have a time-like surface. So I can play the same game for like flat space-times or de Sitter space-times. as long as I have some stretched time lag cutoff surface. Of course, then the actual interpretation is given precisely when you have anti-de Sitter asymptotics. But again, let's go on. So, and the fluid degrees of freedom are now maps that extend between these two boundaries. There are non-local degrees of freedom, like Wilson lines, that are defined, that you can define as, for example, null geodesics that go from one point on the boundary to some point on the horizon. And because they are non-local quantities interpolate in the whole space-time, they are like bifundamental fields. They will transform under the bulk diffeomorphisms only through how the endpoints transform. And the velocity field is given by the push forward of this null vector that we had defined on the null surface through these maps. And so let me be a little bit more precise on how this construction works. So let's think about, I give you a metric. What you have to do is to rewrite the metric in this form, which reminds you of the Eddington-Finkelstein type coordinates. In this form, the null geodesics corresponds to have x equal constant. So because when it's constant, ds square is 0. So these are null geodesics. And when you wrote the metric in this way, then what you can do to construct this null geodesics is to start from a boundary point. And because this is conserved, you reach the horizon at the same point. And therefore, the map itself is given just by the horizon coordinates, or in other words, the embedding coordinates of the horizon. And now here comes the interpretation of the symmetries, because remember, we had these bulk diffeomorphisms, the constrained ones, because they satisfy some horizon boundary conditions. You can either transform the bulk metric or the embedding coordinates. And therefore, because the maps are defined through these embedding coordinates, they transform precisely as these horizon preserving diffeomorphisms. So in other words, like this. Okay, so these green ones are the redundancies of the hydrodynamic theory, and these parts are the symmetries of are the shift symmetries of the dual chaotic theory. So these two parts were postulated just in field theory, and this new part is something that we were not expecting. Okay, so this is basically the end of my talk. So let me just, I hope that I have given you an introduction of the horizon symmetries, the new horizon symmetries, and the interpretation. And there are a bunch of generalization that one can do to charged black holes, extremal black holes, higher derivative and stringent corrections going to non-maximally chaotic system, or non-asymptotically anti-de Sitter spacetimes. But one particularly pressing question is what is the implication of this piece in the symmetry in the dual effective field theory? And in particular, you would have to construct, and this is what we are doing, an effective field theory for chaos that is not just 0 plus 1, that does not entail energy conservation only, but the full energy and momentum conservation, and therefore impose this whole symmetry and try to derive what are the predictions of that theory. And then other things that one can try to see in the same spirit as here, we have provided a holographic dual of the shift symmetry, because this is how you can view also this work, not just as an interpretation of the horizon symmetries from the boundary, but also as the holographic dual of what these postulated shift symmetries in the boundary were in the gravity side. So at the same time, you can think about what is the gravitational dual of the symmetry responsible for entropy production, and whether there is a symmetry responsible for the infinite tower of pole-skipping points. For those who don't know about that, there have been in the literature developments about finding the structure of the pole skipping, not just in the energy sector, but in all the other momentum sector or current sector and so forth and so on. And another interesting question that keeps bugging me is the relation of these horizon symmetries to horizon edge modes, horizon symmetries, horizon edge modes, and hydrodynamic fields. And with that, I would like to thank you.
Any questions from Natalia? Yes.
So yeah, when you go to low T, when you become like near extremal, so is then, in that case, is there some connection to the Schwarzian sector? I'd say that it should secretly be equivalent, basically. That yeah.
Yeah, there should be, but we have not done this connection yet. And that's one of the questions that we have.
And can you write effective action for these extra degrees of freedom and do something analogous to the Schwarzian corrections? Like you get corrections in finite black hole thermodynamics. So would that be relevant, or you think it would not?
Yes, I think that would be relevant because it would be nice to understand like an effective action that arises from, this would be another step to really, I have motivated for you the symmetry construction, but you can also try to derive the symmetries from a holographic action. And you would want to compare this with the Schwarzian sector, also because the Schwarzian sector precisely has this type of symmetries, but they arise in a slightly different way because they are this intrinsically related to the ADS2 sector, while in these general black holes, you don't have that. So I don't really know at this point, but this is certainly one of the next steps.
Mm-hmm. Yeah, that was super interesting. If you can move away like from this ADS2,
yeah.
very special.
Yeah.
Any further questions? If not, let's thank Natalia again. Okay, thank you.
All right. So I guess thank you. See you. Bye.